Swayam Prabha. Digital India. Educated India.
So, welcome to the course on building energy systems and auditing. So, today we are in the module 1 and the lecture number 4. So, today we will discuss about the ventilation and the air properties. If you remember the earlier two lecture, we have properties of material, particularly the thermal properties of material. So, today in the ventilation and the air properties, we will go with this. We will go with the requirement and the types of ventilation, then we will discuss something about the design guidelines of natural ventilation, the heat gain in the buildings and the air and its properties. So, in the requirement point of view, the why the ventilation is required. The ventilation is required for being two cause. One is the human health, because in the indoor we need sometimes a periodical interval some fresh air intake. Just to have maintain kind of the level of the carbon dioxide and oxygen balance, and also we require it to remove the odor, remove some of the gases and all the kind of the some product that may give some kind of a odor or something. The second requirement of the ventilation is for the human comfort. The human comfort because of the sweat, because of the heat, sometimes it is because of the cold. So, we have to maintain a particular temperature which actually soothe a person based on his health, based on his the clothings, etc. So, we require some kind of a periodic ventilations also. Now, if I say the types of ventilation, it is broadly classified into two ways. One is natural ventilation, which actually, as we all know, it is through the air and through the fenestration. It is the outdoor air which comes through because of the typical placement of the inlets and the outlets of the fenestration. And the second one is the mechanical ventilation. It is due to some kind of the fan, the air conditioner, etc. So, by virtue of these two types, we can say that the natural ventilation is energy efficient, whether in case of the mechanical ventilation you need electrical energy to do that. So, now what are the different factors for the natural ventilation? So, we see the first factor is the orientation. The orientation is that a building is oriented in some direction, maybe this is the north and maybe this is the wind, the pattern or so. So, what is the orientation my inlets? So, that is going to be one of the factor. Then the external features, is there is any kind of a building or some kind of external or some trees or something is there or not, and externally that will also create some kind of a barrier to the natural ventilation. Then the position of the window, it is definitely the inlet, and where is the outlet? Is it in the cross side or it is the just opposite side, and that will also demarcate that what will be the type of ventilation, because in case of the natural ventilation the one side it will be a positive air pressure will be created and another side is a negative air pressure will be created. We call that is a windward side positive pressure and the leeward side negative pressure. So, as and when this negative and the positive there is a pressure difference, air pressure difference, it may be a very small difference, but still there should be a difference to maintain a ample amount of flow. Size of the opening, that is definitely one of the criteria. Is it a small opening, is it a large opening, and also the controls of the opening. If there is any kind of a fins in case of any kind of a chhajja, those are also going to play a vital role in case of the amount of the ventilation is in a prevailing in indoors. So, let us first discuss some of the guidelines. I have taken those guidelines from the National Building Code 2016. So, the first of all they say that the fenestration should be oriented at an angle between 0 degree to 30 degree. Please remember that the 0 to 30 degree is this angle or the orientation is based on the prevailing wind direction. It is not with the north or not with the east or west anything, any the codal direction, it is all with the prevailing breeze. In case of the east or west side, it can be oriented at 45 degree to get a higher velocity inside the room. That is also one of the issue. Then the inlet opening in the building should be well distributed. So, it is always better in the windward side will provide the inlet openings and should be well distributed. Maybe the same amount of area, but well distributed, and the outlet opening should be located in the leeward side. Just now I have discussed with that, because we need to create a kind of a pressure difference between the inlet and the outlet, otherwise there will be not so much of the wind flow inside. The maximum air velocity at a particular plane is achieved by keeping window of following recommendations. So, there are if your building has some kind of the level of occupancy, if it is sitting in chairs, maybe it is a classroom scenario, then 0.75 meter is the lowest level of the opening can be think for. If it is a sitting on our bed or something like that, we can lower down the sill level a bit of 0.6 meter or so. If it is a sitting on floor kind of a scenario, maybe some primary school or something like that for the kids. So, we can further do little bit below the sill level, such a way that the inlet level starts from 0.4 meter or so. The room of normal size, we know we can go for some kind of the windows in the opposite direction or maybe the cross direction or the adjacent directions. So, what we can say from here is that if want to have a kind of a good ventilation, so the width of the window can go up to the 2/3 of the wall, 2/3 of the wall. So, 1/3 may be the solid the wall and 2/3 may be the window. So, that is the maximum we may go. Beyond that, there will be no such of increment. And the greatest flow per unit area will be definitely going to be obtained if the inlet and outlet is the nearby almost equal area. So, that will create a kind of a good pressure difference. The last one, maybe we can say that in case of the rooms or maybe in case of the if any kind of a room is having only one side wall, one wall exposed to the outside, and we can give only one side windows. So, we should give at least 2 windows, that a kind of a circulation may obtain. Suppose this is the only one room, so I want to give 2 at least, some kind of a circulation may attain to in the room or so. So, that is the recommendation. The last one is that because of the sash, because of the canopies, because of the louvered, or sometimes we put some kind of a net to prevent the entry of the mosquitoes. So, those all additional attachment with the windows will change the amount of the natural ventilation, and also that will be going to change the pattern of the ventilation's airflow inside the room. So, now as per that NBC and also SP 41. So, this is an interesting curve. In the x axis it has mentioned that fenestration area in percentage, how much percentage of the fenestration area based on the floor area. So, that is one of the very good measure when we design any kind of a building. So, we can say that it can be tentatively we can keep 20 to 30% of the window area as per the floor area point of view. Beyond that, if you increase the window area to more than 30, maybe around 40s or so, it may not go that sharp increase, we are not going to see that much of which we can get the 20 to 30%. But below 20%, that is very, very poor. So, 20% to 30% of this floor area, the fenestration area with respect to the floor area is good or optimum, we can say. So, that is one of the point, and next point is we have seen that in kind of the size of the inlet, how much will be the size of the inlet and all. The size of the inlet should keep around 30 to 50% of the total area of the opening. So, that means there are two fenestration we may say, some will be actually in the windward side, which I can say that is the inlet, and one will be in the leeward side or maybe the adjacent side, which will be I called as the outlet. So, total area of the windows will be the area of the inlet plus the area of the outlet, but the area of the inlet should be 30 to 50% of the overall area, such a way that it will increase the efficiency of the pressure of the velocity or the total intake of the ventilation. So, we will do a small problem on that. This problem was asked in the 2018 GATE examination air paper, architecture paper. So, it was given that there are two such openings P and Q, which is in opposite side, and those are the inlet and outlet are of 2 meter square of the each area. So, there are total 4 meter square area, 2 for the inlet and 2 for the. So, this is your 2 meter square and this is your 2 meter square of area. The outdoor wind speed is almost about 5 meter per second. The coefficient of the effectiveness, which we have just mentioned here, which is the efficiency, that is 0.6, 0.9 or whatever. So, here it is given as the 0.6. So, rate of ventilation through the enclosure due to the wind condition we have to find out in cubic meter per hour. So, per hour how much cubic meter can be flow inside the room based on the average wind speed of 5 meter per second outside and a 2 meter square the inlet area, 2 meter square outlet area, and effectiveness is 0.6. So, as effectiveness is 0.6, I can say that even though there is a wind speed of 5 meter per second in the outside, only 0.6 times 5 meter square will be taken into the inside. So, the inside velocity which will actually pass through the inlet will be almost about 3 meter per second, because 0.6 times 5. And now I know the area. So, if I multiply the area into the velocity, I know how much cubic meter per second is the entry. So, I can now find out that, because I know the area is 2 meter square, that is only the inlet area. Do not take both the areas, because the flow is from here windward side, which is 5 meter square per second. So, here from it will actually go with the 3 meter square per second because of the ratios or whatever. So, 3 into 2, 3 is the velocity and this is the area and this is the from second to hour I have converted. So, the answer will be almost about 21,600 cubic meter per hour. Okay, very easy, but you need to know the what to do and how to actually deal with this kind of a problem. So, now the convection is as we discussed in the very second lecture, in the very first slide, there are 3 types of the heat transfer. One is the conduction, we have discussed that one. We also discussed the radiation in the last lecture, and the convection. Convection is the way a fluid, particularly in our building, the air actually takes the heat from one place to the other. It may be from the natural ventilation, so the place is outside to inside, or maybe it is the air conditioning, that is from the air conditioning plant where the chilled air is actually going to create it, or maybe the AHU where it is created, and from there it is the inside. So, there is a change of the state or the temperature of the air from one side to the other side. The rate of ventilation, if I know as V, that is the ventilation rate, if I know as V, that is meter cube per second, how much meter cube per second the air is entering in a particular space. If I want to know that, if I know that, and if I know what is the delta T, that means the temperature difference between the outside air and the inside air, or maybe the treated air and the outside air, whatever may be, that there is definitely a temperature difference, because I do not want to from the air conditioning take the whatever the outside air temperature same inside, we have to chill it down, cool it down. So, there is a delta T. So, if I know these two values, ventilation rate and the amount of temperature changes, I directly can multiply with 1300, which is the volumetric specific heat of air as given as joule per meter cube per degree C, degree centigrade. So, I can find out the how much is the heat comes in for this particular rate, I mean for the heat rate, flow of heat rate due to the convection. So, number of air exchange, that is another issue. So, we have told that we need to have some kind of air exchange per hour or so, and if I know the volume of the room, I can find out this rate of air exchange as number of exchange per room multiplied by the volume of the room, and that is divided by 360. So, here some of this SP 41 also, that the same thing has been given in the NBC. The air exchange per hour is recommended for various spaces. Suppose it is a classroom like your classroom or maybe laboratory or somewhere, it is 3 to 6 air exchange per hour. That means 3 to 6 times the whole volume of your classroom has to be changed by a fresh air, 3 to 6 times in an hour. So, you need to know the volume of your classroom, you need to multiply that one with 3 or 6 whatever may be the exchange rate and divide that by 3600. So, you can get the how much meter cube per second is your V. In bedrooms it is again 3 to 6, in case of bathrooms, toilet is a little high, 6 to 12, in case of the cafeterias and the restaurants there are a lot of the smokes and all those things. So, the air exchange is too high, 12 to recommended is too high, 12 to 15, the cinemas is 6 to 9, like that. So, the small problem we can solve, suppose a room is measuring 12 meter by 25 meter by 4 meter and it is mechanically ventilated through a treated outside air, and you see the outside air temperature is 38 degrees centigrade, whether the room has to be needed to be a temperature of 24 degrees centigrade. So, I want to drop that particular outside air temperature 38 to 24, almost like 14 degrees or so. If room needs a 3 air exchange per hour, so I have to find out the energy requirement. So, air exchange per hour is 3 and I know this is the volume, 12 multiplied by 25 into 4 and divided by 3600 total number of seconds per hour. So, I know V, this V is your 1 meter cube per second, and then I will apply the second formula, which is the Q into V into del T, Q equal to 1300, that is the specific volumetric specific heat, 1 is your this V air exchange rate and this is the del T. So, I will find I got the 18.2 kilowatt hour is the energy required for this particular ventilation. Now, let us go to the heat gain in the building. So, building will get lot of ways of heat gain. We can actually say there are two major ways. One is the external heat gain, those we have just now discussed, conduction, convection and the radiation through, and also due to the internal occupancy, internal some instruments, some lighting etc. also provide some kind of the heat gain. We will discuss in the next module those heat gains and those kind of the internal heat gain. So, those are the typical some of the parameters for the internal heat gains also. So, we can see those changes, there are a lot of other changes, but if you see the internal heat gain, we have two type of the heat, one is the sensible heat and one is the latent heat, both has to be added together to see the space is how much is the total heat gain also. Now, what is the sensible heat? It is the heat which actually absorbed without change of any kind of a state. So, it increase the temperature because of the sensible heat. Okay, it is some object, some solid object is increasing its temperature because of the convection, conduction and the radiation, there is some changes of the temperature we notice. So, due to that it is the sensible heat, we will just see the change of temperature. In the sensible heat, if there is any increase or decrease, or we can see there is a change of temperature. So, the sensible heat loads are based on actually basically from the building envelope due to the infiltration of the outside air. There may be you have a totally concealed area, but there is slight infiltration of air from outside. There is a solar heat gain through the glasses and windows, appliances load and occupancy of the body heat. So, those are also there. But what is the latent heat? Latent heat is actually due to the moisture, the air vapor that also present in that, and that is because of this contain some kind of a latent heat because it is in the state of the vaporized state. So, from one state to another you require latent heat for any kind of the liquid, maybe if it is for the water. So, from the liquid to the vapor there is a kind of a latent heat, but latent heat cannot be actually measured by the thermometer, or the temperature increase or decrease, it cannot be seen. So, latent heat, how it will be actually came in, or it will increase the internal load of a building or a space, or so it is a moisture. Definitely when there is a air comes in, there is some kind of a moisture coming, there is a occupant respiration and the activities, that also giving some kind of a sweating, some kind of a breathing and all those, that also has some kind of a moisture. And also there are some moisture from the equipment at the appliances. Suppose you are cooking something, you are doing some kind of a washing something, clothes and all in a machine. So, definitely there is a moisture coming out of it. So, that also increase some of the load, some of the heating load in the particular space. So, in the air and air property, so what is the air? Air is a kind of a mixed gases, it has nitrogen, it has oxygen, almost 78% of the air is with nitrogen, 21% is almost with oxygen, it has some amount of argon, it has some amount of carbon dioxide, and also it has some amount of water vapor and also dust particle. So, these all are actually the air. So, in the air I can actually visualize the air in this diagram, where these green dots are some of the air molecules. So, green dots are your nitrogen, maybe it may be your oxygen, it may be your all those carbon dioxide or maybe dust particle, anything. And there are some the white colored dots, which is a space for the moisture. So, you may fill all the spaces with the moisture or you may not, and those yellow dots are of your water molecule, that this moisture molecule. So, within this three phase, this is, you can say it is a three phase diagram of air, where there are air molecules, there is some space for the moisture available and some space of course that will be filled with the water also. So, in this point of time, if I say this is a temperature are actually defined as, are actually measured as, not defined, as two types, and the dry bulb temperature. So, I take a particular thermometer and there is a bulb where the mercuries or all these things are there. So, that bulb is dry, nothing is there. So, whatever the air passes through that particular dry bulb, it actually notices that temperature and it will rise that particular mercury in a certain level or certain height. So, from there I can find out what is the temperature of the air flow. Similarly, if I want to find out the wet bulb temperature, so what I will do, I just put that particular bulb in a wet clothing or something, okay. And if there is a air flow through it, the air will actually take out some kind of a moisture from those wet clothing, which is in and around that particular bulb. So, what happened, it will be evaporative cooling will be there, and gradually there will be a drop of temperature with respect to the DBT. So, DBT is maybe 40 degree, but when the other temperature device is having some kind of a wet clothing, so because of the evaporative cooling, this will be going to be dropped. So, the wet bulb temperature is because of this particular phenomena, this particular phenomena of the temperature reduces because of the evaporative cooling. The last line is very important, the wet bulb temperature is always less than the DBT. Definitely that is because of the evaporative cooling effect. Now, suppose the air is very dry. So, there is not a much of the humidity or the moisture content in the air. So, if I just pass through a particular dry air through the wet bulb thermometer, there will be a huge amount of drop, because the air has a lot of vacancies, I may say, lot of vacancies. So, it can actually absorb lot of moisture from that particular the wet cloth, and gradually the evaporative cooling amount of cooling will be increased and there is a drop. So, we will have a higher drop. But if the water is humid, water is moist air, so that particular water does not have that much amount of vacancies. So, it will pass through and it will take a minimum amount of moisture whichever it is available or required or to fill that particular excess amount of the vacancies. So, the drop of the the wet bulb temperature will be little less or less with compared to the dry air. So, we can say that this dBT WBT drop will be very high if the air is dry. So, that means we can say dry air means the very less humidity, less amount of the relative humidity. So, in case of the less amount of relative humidity, this drop is very high, whereas if the already it is very humid air, already the relative humidity is very high, more than 80% or so, there will be very little amount of drop between the WBT and the dBT. So, by virtue of this drop, how much is the drop between the dBT and WBT? I will say this RH is low and I can say this RH is high, is not it? So, this RH, and I can actually figure out that what will be this relation between this dBT WBT drop with this RH. So, that also can be figured out in the way that I can find out this particular RH from the these two kind of scenarios or so. So, that I have told you that in general dBT is higher than WBT. So, that is fine, and this dBT WBT drop will give you a kind of a understanding of how much moisture a particular air is containing. That means how much relative humidity is having that particular state of the air, and that will be beneficial for us we need to know two very the important parameter of the air. One is the temperature and one is the relative humidity. Now, suppose this dBT and WBT is same. I am going to suppose I am finding both the temperature, this temperature, the instrument, the both are suppose same. That means the air is fully saturated. So, if the moist air is passing through, it is not at all even taking even a one molecule of the moisture to take in to the air space, because there is no air vacancy, no air space vacancy. So, it is fully saturated. So, the RH is almost 100% or so. So, we will discuss in that particular diagram. So, we have already discussed that one. Suppose in the x axis I have plotted the dBT, y axis is the WBT. Suppose these are the values. So, both the dBT and the WBT are same. So, that means it is a case of full moist condition. So, there is no such of the vacancies are left. So, this I can plot a line. Of course, in generally line is not a straight line, it is a curved line. So, we will discuss in the next lecture. So, but theoretically we can say that there can be a line. So, in that line what we can say, it is equal dBT and WBT, number 1. Number 2, there is no drop between the WBT and dBT because both are same. So, water vapor is saturated. So, if I see my 3-phase diagram, no space, moisture space is vacant, all are filled by yellow water, the yellows, that means the water molecule, right. Now, in some of the cases we may say these blue lines are there, blue dots are there. So, that means for the dBT 20 degree, WBT is 10 degree. So, WBT is less than dBT and there is a little bit of the gap, not exactly they are same. This is 22 degree and 30 degree, this is 40 degree and 27 degree. So, we can say that in this scenario, the dBT as WBT are not equal, number 1. There is a dBT WBT drop is exist, number 2, and number 3 is that if there is a drop exist, even if it is the smallest amount of drop, there is some vacancies are there. So, that is why there is a drop. So, water will the air will try to collect some of the molecules of the air from this WBT, this wet clothes. So, the 3-phase diagram will look like this. There are some spaces available, of course, some spaces are also filled. So, any such lines can be drawn from here, and from that we can find out the relative humidities and all those kind of a thing. You go away from this 45 degree line, your RH is low, and if you go higher, RH is high. So, but one thing we can say that dBT cannot be more than WBT, there cannot be any line the upper side 45 degree line or so. So, that is all for today's lecture. These are the references. So, what we understand is that the natural ventilation is a important feature and that can be adopted for energy conservation. So, there is a typical ratio and the total area versus the floor area parameters of the inlet and outlet. Two type of heat exist in normally, one is called sensible and one is called the latent heat, and dry bulb temperature, wet bulb temperature is give you a indication of the relative humidity, which is one of the prime factor to understand the ventilation, particularly the mechanical ventilation. Thank you very much.